Table 310.16, found within the National Electrical Code, is specifically tailored for alternating current or AC circuits and is not applicable to direct current or DC systems. This distinction arises from fundamental differences in how electrical current behaves in AC versus DC circuits. In AC systems, the current flow periodically reverses direction, typically at a rate of 60 Hz in North America, meaning 60 cycles per second. This alternating current flow induces effects such as skin effect and inductive reactance, which influence the current distribution within a conductor and its overall impedance. These factors are considered when determining the ampacity or current carrying capacity of conductors in AC circuits, as reflected in Table 310.16. Conversely, in DC systems, the current flows in a single direction constantly. As a result, phenomena like skin effect and inductive reactance are either absent or negligible. Skin effect, in particular, causes AC current to concentrate near the surface of a conductor, effectively reducing the conductor's cross-sectional area available for current flow and increasing its resistance. Since DC current distributes more uniformly throughout the conductor's cross-section, the ampacity dilating factors associated with skin effect do not apply. The National Electrical Code, or NEC, provides guidelines and tables specifically designed for determining the appropriate conductor size and ampacity for various wiring configurations and environmental conditions. Table 310.16 is a key component of these guidelines, providing ampacity values for insulated conductors rated up to 600 volts, installed in raceways, cables, or directly buried in the earth, based on an ambient temperature of 30 degrees Celsius, which is 86 degrees Fahrenheit. The table considers factors such as conductor material, insulation type, and the number of current-carrying conductors in a raceway or cable. However, the ampacity values listed in Table 310.16 are derived from calculations and testing procedures that account for the unique characteristics of AC circuits, including the effects of impedance and skin effect. Applying these values directly to DC circuits would be inappropriate and could lead to inaccurate and potentially unsafe installations. For example, using Table 310.16 to determine the conductor size for a DC circuit could result in undersized conductors, which could overheat and potentially cause a fire. Conversely, it could also lead to oversized conductors, which would be unnecessarily expensive. Therefore, it is crucial to use appropriate ampacity tables and dilating factors specifically designed for DC circuits when designing and installing DC electrical systems. While the NEC does not provide a direct equivalent to Table 310.16 for DC circuits, it does offer general guidelines and requirements for conductor sizing and overcurrent protection in Chapter 3, Wiring Methods and Materials, and Chapter 2, Wiring and Protection. These guidelines emphasize the importance of considering the specific characteristics of the DC circuit, such as the voltage, current, load type, and operating environment when selecting conductors and overcurrent devices. In addition, other industry standards and engineering resources provide more detailed information and guidance on ampacity calculations and dilating factors for DC circuits. These resources often take into account factors such as conductor material, insulation type, ambient temperature, and the presence of harmonics or other non-sinusoidal currents. When working with DC circuits, it is essential to consult these resources and apply appropriate engineering principles to ensure that the conductors are properly sized and protected. Furthermore, it is important to consider the specific application and operating conditions of the DC circuit when selecting conductors and overcurrent devices. For example, in photovoltaic or PV systems which generate DC power from sunlight, the conductors must be sized to handle the maximum short-circuit current of the PV array. Similarly, in battery-based DC systems, the conductors must be sized to handle the maximum charging and discharging currents of the batteries. In these types of applications, it is crucial to follow the specific requirements and recommendations outlined in the NEC and other relevant standards. In summary, Table 310.16 is not applicable to DC circuits because it is specifically designed for AC circuits and takes into account factors that are not relevant to DC systems. When working with DC circuits, it is essential to use appropriate ampacity tables and derating factors, consult relevant industry standards and engineering resources, and consider the specific application and operating conditions of the circuit to ensure safe and reliable operation. The behavior of electrical current in alternating current, or AC, and direct current, or DC, circuits differs significantly due to the nature of how the current flows. In AC circuits, the current periodically reverses its direction, typically at a frequency of 60 Hz in North America. This changing direction of current flow gives rise to phenomena such as inductive reactance and skin effect, which influence the distribution of current within the conductor and the overall impedance of the circuit. Inductive reactance is the opposition to the change of current flow in an AC circuit, and it is directly proportional to the frequency of the AC signal and the inductance of the circuit. Skin effect, on the other hand, causes the AC current to concentrate near the surface of the conductor, reducing the effective cross-sectional area available for current flow and increasing the conductor's resistance. These effects are taken into account when determining the ampacity of conductors in AC circuits, as reflected in tables like 310.16 in the National Electrical Code. In contrast, DC circuits involve a constant flow of current in a single direction. This unidirectional current flow eliminates the effects of inductive reactance and skin effect, simplifying the analysis and design of DC circuits. Since the current is evenly distributed throughout the conductor's cross-section in DC circuits, the ampacity derating factors associated with skin effect do not apply. Therefore, the ampacity of a conductor in a DC circuit is primarily determined by its material, size, insulation type, and the ambient temperature. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, but it is crucial to understand that certain tables, such as 310.16, are specifically intended for AC circuits and should not be applied directly to DC circuits. Table 310.16 lists the allowable ampacities of insulated conductors rated up to 600 volts, based on their size, insulation type, and installation conditions. The values in this table are derived from calculations and testing procedures that account for the specific characteristics of AC circuits, including the effects of impedance and skin effect. Applying these values to DC circuits could lead to inaccurate and potentially unsafe installations. For example, using table 310.16 to determine the conductor size for a DC circuit could result in undersized conductors, which could overheat and cause a fire hazard. Therefore, it is essential to use appropriate ampacity tables and derating factors specifically designed for DC circuits when designing and installing DC electrical systems. While the NEC does not provide a direct equivalent to Table 310.16 for DC circuits, it does offer general guidelines for conductor sizing and overcurrent protection in Chapters 2 and 3. These guidelines emphasize the importance of considering the specific characteristics of the DC circuit, such as the voltage, current load type, and operating environment when selecting conductors and overcurrent devices. In addition to the NEC, other industry standards and engineering resources provide more detailed information and guidance on ampacity calculations and derating factors for DC circuits. These resources often take into account factors such as conductor material, insulation type, ambient temperature, and the presence of harmonics or other non-sinusoidal currents. When working with DC circuits, it is crucial to consult these resources and apply appropriate engineering principles to ensure that the conductors are properly sized and protected. Furthermore, it is important to consider the specific application and operating conditions of the DC circuit when selecting conductors and overcurrent devices. For example, in photovoltaic or PV systems, which generate DC power from sunlight, the conductors must be sized to handle the maximum short-circuit current of the PV array. Similarly, in battery-based DC systems, the conductors must be sized to handle the maximum charging and discharging currents of the batteries. In these types of applications, it is crucial to follow the specific requirements and recommendations outlined in the NEC and other relevant standards. The ampacity of a conductor, which is the maximum current it can carry continuously without exceeding its temperature rating, is a critical parameter in electrical design. The ampacity of a conductor is influenced by several factors, including its material size, insulation type, ambient temperature, and installation conditions. The NEC provides tables, such as 310.16, that list the allowable ampacities of conductors under specific conditions. However, it is important to understand the limitations of these tables and to apply appropriate dirting factors when the actual installation conditions differ from those specified in the table. For example, if a conductor is installed in an area with a high ambient temperature, its ampacity must be derivated to account for the increased heating effect. Similarly, if multiple current-carrying conductors are installed in the same raceway or cable, their ampacities must be derivated to account for the mutual heating effect. The NEC provides specific dirting factors for various installation conditions, and it is essential to apply these factors correctly to ensure that the conductors are properly sized and protected. In addition to ampacity, the voltage drop in a conductor is another important consideration in electrical design. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting the voltage drop in branch circuits to 3% and the total voltage drop in feeders and branch circuits to 5%. To minimize voltage drop, it is important to use conductors that are large enough to carry the required current without excessive voltage drop. The voltage drop in a conductor can be calculated using Ohm's law, which states that voltage drop equals current times resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. The NEC provides tables that list the resistance of conductors of various sizes and materials. By using these tables and Ohm's law, it is possible to calculate the voltage drop in a conductor and to select conductors that are large enough to meet the voltage drop requirements. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from damage caused by excessive current flow. These devices interrupt the flow of current when it exceeds a predetermined level, preventing overheating, insulation damage, and potential fire hazards. The NEC requires that all conductors be protected by overcurrent devices that are sized to protect the conductors from overloads and short circuits. The size of the overcurrent device is typically based on the ampacity of the conductor it is protecting. However, there are certain exceptions to this rule, such as when the conductor is part of a motor circuit or when it supplies a specific type of equipment. The NEC provides detailed requirements for overcurrent protection in Chapter 2, Wiring and Protection. These requirements specify the types of overcurrent devices that are permitted, the methods for sizing overcurrent devices, and the locations where overcurrent devices are required. In summary, when designing and installing electrical systems, it is essential to understand the principles of ampacity, voltage drop, and overcurrent protection. The NEC provides comprehensive guidelines for these aspects of electrical design, but it is important to understand the limitations of these guidelines and to apply appropriate engineering principles to ensure that the electrical system is safe, reliable, and efficient. The differences between AC and DC circuits extend beyond the behavior of current flow. They also impact the selection of components, the methods of protection, and the overall system design. For example, capacitors, which store electrical energy in an electric field, behave differently in AC and DC circuits. In a DC circuit, a capacitor acts as an open circuit once it is fully charged, blocking the flow of current. However, in an AC circuit, a capacitor allows current to flow, with the amount of current depending on the frequency of the AC signal and the capacitance of the capacitor. Similarly, inductors, which store electrical energy in a magnetic field, also behave differently in AC and DC circuits. In a DC circuit, an inductor acts as a short circuit, allowing current to flow freely. However, in an AC circuit, an inductor opposes the flow of current, with the amount of opposition depending on the frequency of the AC signal and the inductance of the inductor. These differences in the behavior of capacitors and inductors in AC and DC circuits are important considerations when designing electronic circuits and power supplies. The methods of protection used in AC and DC circuits also differ. In AC circuits, ground fault circuit interrupters, or GFCIs, are commonly used to protect against electric shock hazards. GFCIs detect small imbalances in the current flowing through the hot and neutral conductors, which can indicate a ground fault. When a ground fault is detected, the GFCI quickly interrupts the flow of current, preventing electric shock. However, GFCIs are not effective in DC circuits because they rely on the alternating nature of the current to detect ground faults. In DC circuits, other methods of protection, such as fuses and circuit breakers, are used to protect against overcurrents and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing overheating, insulation damage, and potential fire hazards. The overall system design of AC and DC electrical systems also differs. AC systems are typically used for power distribution because they can be easily transformed to different voltage levels using transformers. Transformers are devices that transfer electrical energy from one circuit to another through electromagnetic induction. They can be used to step up or step down the voltage, allowing power to be transmitted over long distances at high voltage levels and then step down to lower voltage levels for use in homes and businesses. DC systems, on the other hand, are typically used for applications where energy storage is required, such as in battery-powered devices and electric vehicles. DC systems are also used in applications where precise control of voltage and current is required, such as in laboratory equipment and industrial processes. In summary, AC and DC circuits differ in many ways, including the behavior of current flow, the selection of components, the methods of protection, and the overall system design. Understanding these differences is essential for designing and installing safe, reliable, and efficient electrical systems. The NEC provides comprehensive guidelines for both AC and DC electrical systems, but it is important to understand the specific requirements for each type of system and to apply appropriate engineering principles to ensure that the electrical system is properly designed and installed. When working with electrical systems, it is always important to follow safe work practices and to wear appropriate personal protective equipment, or PPE. Electrical hazards can be deadly, and it is essential to take precautions to protect yourself from electric shock, arc flash, and other electrical hazards. Before working on any electrical equipment, it is important to de-energize the circuit and to verify that the circuit is de-energized using a voltage tester. It is also important to use insulated tools and to wear appropriate PPE, such as gloves, safety glasses, and flame-resistant clothing. Arc flash is a dangerous phenomenon that can occur when a short circuit or other electrical fault creates a high-energy arc. Arc flash can cause severe burns, blindness, and even death. To protect against arc flash hazards, it is important to perform a hazard assessment and to select appropriate PPE based on the potential arc flash energy. The NEC provides guidelines for arc flash hazard assessments and for selecting appropriate PPE. In addition to following safe work practices and wearing appropriate PPE, it is also important to be aware of the potential electrical hazards in the workplace and to take steps to mitigate these hazards. This includes identifying and correcting any electrical code violations, ensuring that electrical equipment is properly maintained, and providing training to employees on electrical safety. Electrical safety is a shared responsibility, and it is important for everyone to work together to create a safe working environment. The Occupational Safety and Health Administration, or OSHA, provides regulations and guidelines for electrical safety in the workplace. These regulations cover a wide range of topics, including electrical wiring, grounding, overcurrent protection, and personal protective equipment. Employers are required to comply with OSHA's electrical safety regulations and to provide a safe working environment for their employees. Employees also have a responsibility to follow safe work practices and to report any electrical hazards to their employer. By working together, employers and employees can create a safe and healthy workplace and prevent electrical accidents.